So we ended on a discussion of the triple line. Whenever we're dealing with, there's this curve basically in between the liquid vapor and the solid vapor region on both surfaces that contract on freezing and surfaces or substances that expand on freezing. Now, this is, these are both PV diagrams, and we would see this line also on TV diagrams, temperature versus volume. Now, there is a third combination, a third set of dimensions there, if you will. And if I could, let me say that I've got, let's say I hold this paper in 3 dimensions. Okay? So there's a statement here that says this becomes a single point when viewed on the PT diagram. So let's say that this sheet of paper basically represents the saturation dome, if you will. Okay? So notice that this line, the top of the paper, appears as a line if I view it this way, right? Or if I view it this way. It also still appears as a line. However, if I turn it this way, and granted, come with the sharp edge at you, right? Notice that if I can get this, and I can't quite get it right straight at the camera, but notice that you no longer see the line, you just kind of see this point, you see that corner. When you view something that's a line viewed in 2-dimensional planes, when viewed from a third direction, it becomes a point. Right? And the same thing for, again, if you consider this sheet of paper similar to like the saturated dome region, then it's going to be, when viewed from this direction or whether viewed from this direction, it's going to appear kind of as a flat surface. But if I view it in the third dimension, if you will, and it's really all I'm going to see is this curve. It's a lot easier to show this in the classroom. There we go. So it really, this surface becomes just a curve, a line, if you will, when viewed from the third dimension. So if you've had statics or you've had multivariable calculus, that's probably, I'm sure you've probably experienced that a little bit in those courses. If you've had a graphics class where we talk about 3-dimensional CAD or 3-dimensional graphing, and then maybe those help as well. If it's your first exposure to 3 dimensions, I apologize. I know that's really probably not a good description, but hopefully it helps a little bit, right? So again, here we're going to look at what we call the PT diagram. That is pressure over here, temperature down there. And so we're viewing now the edge. So this is the saturation dome, the vaporization dome, the division between the liquid region and the vapor region. So when viewed from the edge, when I just look at the edge of that dome, I just see a curve. Okay? And up here's our critical point, the top of the curve, and the bottom of the curve between the vaporization and what we call the sublimation curve. That is the triple point when viewed on this diagram. It's a triple line when viewed from the other diagrams. Now, I've put a reference point down here just to kind of help you out with how this graph works. Again, the general shape of the graph is going to be true for any substance. The only difference is just the scale, what values these fall at. For carbon dioxide, you would need to go look up the triple point for water. I don't know what it is, but for carbon dioxide, the triple point right here would be 5.1 atmospheres and minus 57 degrees Celsius. That's pretty cold, but that's 5 atmospheres. That's 5 times the atmospheric pressure. Here in 1 atmosphere, so if I went to the store and bought a hunk of dry ice to rapid freeze some fruits or some meats to better preserve them, so it basically is right here. If you've ever had dry ice, you know it immediately goes from a solid to a vapor. So 1 atmosphere down here Right, so if I plotted 1 atmosphere for dry ice, that would be down here in this sublimation region. So it's going to be a solid, and all of a sudden it's going to be a vapor, and it's not even going to pass through the liquid phase. That's up here. And again, in carbon dioxide, dry ice, so to speak, that occurs at a minus 78 degrees C, very, very cold. Okay, so the triple point is all the way up here at 5 atmospheres, and minus 57 degrees C. If it's water, of course, it's your whole scale changes there a little bit. All right, so just something to think about. Okay, and as I've kind of alluded to, this you're dealing really with a 3-dimensional surface. You're dealing with a 3-dimensional function. This is what, if we combine those 3 graphs, the pressure versus volume, the temperature versus volume, and the pressure-temperature graphs, we combine them all 3, you get a 3-dimensional view. And this would be the PVT surface for substances that contract on freezing. Again, water expands on freezing, so it looks a little different. For water, this region here would kind of push out a little bit. It would move up into the higher volume region. Surfaces that contract on freezing, this area kind of recedes back in. But again, if you've not had any multidimensional studies before, I know when I took a calculus with multiple variables course, they taught us when we're trying to graph a surface to draw sketches, to draw, you know, the XY plane, and then draw the YZ plane, and then the ZX plane. What does this look like from those graphs? And then pick values and draw other sketches. So if we do that, if I say, well, this is pressure and this is volume, kind of this up and this is vertically up and down is pressure, and this kind of up and to, you know, let's say down and to the right is increasing volume, so up and to the left is decreasing volume. So this chart right here, this PV diagram, would be what would happen is if I looked right straight down, if you will, the temperature axis. If I looked right up into the direction of temperature, this would be the projection that I would see. Okay? And if I looked at another side angle, or I guess a top angle, if I'm looking straight down at this thing, looking down the pressure axis, where all I'm going to see is the temperature axis and the volume axis. And what does that look like? Well, that looks like the TV diagram we started with, we described early on. And then again, finally, if I view from this side where I'm looking down the volume axis, I'm just looking at pressure and temperature, I'm going to get this kind of view here. Okay. Now, often the PT diagram is referred to as the phase diagram, because given a pressure and a temperature, I can just go figure out where am I in relation to the vaporization curve or the sublimation curve, depending on what I need information for. But again, if you view this right straight on, your sublimation curve right here between vapor and solid represents this bottom part of the dome region. That's what this curve right here is. So we're really just seeing this little edge right here. The vaporization curve is this dome region right here. We're just seeing this edge right here. That's what those represent. And as you can see, they put the melting curve on for both contract and expand on freezing substances there. So what does all this do for us? Well, here's the idea. You know, Steve, why in the world do we even care about all this? Again, remember, this comes back to the first law, right? So the first law says that if I know what energy comes in and goes out, then I have to track the difference between those quantities gets tracked as the change in energy of the system. Well, if I've got a system that's not moving and it's stationary, so it's not changing kinetic or potential energy, all of these energies crossing the boundary result in a change in internal energy. How do we determine the change in internal energy? Well, we have to know where are we on this surface. Now, the good news is we're not going to draw this surface out in 3 dimensions and plot out exactly where we are on that surface every single time. We're not going to draw it by hand. We're going to do it mathematically using the tables in the back of the text. But as far as actually drawing this out and plotting a point on this surface, no, we won't do that. Not physically, just mathematically, so to speak. But I do need to know what is my phase. I need to know, am I here in the vapor region? Am I in the liquid region? Am I dealing with a solid? Where am I in relation to the critical point? If I'm beyond the critical point, notice they've labeled this the gas region. So if I'm up in here beyond the critical point, I can often refer to that as the ideal gas region. I can treat it as an ideal gas, and things become very simple. But you have to know that to make that assumption. So, why is this important? Well, because I need U values. To get U values, I need to know what I'm dealing with. And most of the time, I'm not going to know. I'm just going to know a couple of properties. 2 properties is normally all I need. On rare occasion, I might need 3. And that's kind of the whole. That would be, let's see, that would pretty well finish up Lecture 3. That would bring us in, I'm sorry, Lecture 5. That would pretty well bring us into Lecture 6. So normally I break Chapter 3 into 2 75-minute lectures, but it's summertime, so I'm getting them all done at once. So this would move us kind of in that Lecture 6 phase of the section. So if you've been watching these videos straight, this wouldn't be a terrible place to just pause, get up, use the restroom, move around, and come back. I'm going to keep going, but if you need to pause, I will understand. So, our goal here is to try to quantify specific energy, U, lowercase u value. Later on in the course, we'll also need H values. We call those enthalpy and entropy values for the second law. So, we will need other properties, but we'll find those the same way we'll find U values. So again, there's not necessarily, for water in R134, we're not going to have an equation for U is equal to this stuff, and we solve for U. No, it doesn't work that way. We're going to use property tables because they're a lot more effective at communicating the complexity of what's going on. Okay. Now, so like I said, this is normally where, now you can discard those. This is normally where we would switch between lectures. So let's see here. Lecture 6. Okay. So again, equations to determine things like U and S, the entropy value, are typically complex, and it's more practical to publish tables. Now I'm going to turn my view on there so I can see what I'm showing you. Alright, so if you go to the back of your text, and I've made these available on Canvas for my class. If you go into the modules, down at the bottom of the modules page, you should see a PDF that says something about property tables, 6th edition. Now these are the 9th edition property tables. I just happen to have a PDF of the 6th edition laying around. Feel free to print those out and use those for personal educational use. Obviously don't sell those. Let's not get a cease and desist letter from the publisher here. But anyway, at the back of your text in the 9th edition, this starts about page 881 is where this starts. There's Appendix 1, that is the SI units. And if we flip through here, the table A1 over here is going to be a very valuable table for you anytime I'm dealing with an ideal gas. In Chapter 4, we're going to talk about the specific heats. So that's tables A2, 3, and up to A4. A4 is where we start talking about water. So that is saturated water, the temperature table. Notice this far column over here is nice, round temperature values. It's going to be tough to do without. Okay. These are nice round temperature values. I know you can't see this very well. The hope is you've got your book you're looking at, or you print out the property tables that I've made available to you, and you look through those or pull them up on a PDF on another device. Have some way so when you're working your homework, you've got those next to you. So again, table A4 is saturated water temperature values on the far left column. Nice round temperature values on that. The next table is table A5, and I'm going to stop there. We'll pick up talking about table A5 on the next one. Loud pop.